Hi everyone. So it's fairly straightforward to show using Gauss's law that there is no gravitational field between two infinitely large uniform slabs of mass. And of course you can make a similar statement about the electric field in electrostatics. But what I wanted to do in this video was to look at the same result from a different perspective and explain why there is no field in this case, using an arguably simpler logic which relies purely on the fact that gravity is an inverse square law type force. So what we're going to do is to choose some arbitrary point that lies between the two slabs. Let's say we are going to focus on this point here and consider the gravitational field at that particular point due to the slabs by imagining splitting up each of the slabs into infinitely many infinitesimally small mass elements and reasoning about how those contributions of the small mass elements combine together. So I've just arbitrarily drawn on our first mass element that we're going to consider the contribution of there. Let's start defining some parameters. I'm going to draw a line of sight from the center of that element to the point that we are interested in, and say that that distance, the length of that blue line, is r1, so let's label that. But now that we've got our first arbitrarily chosen mass element, which mass element should we look at next? Well, a fairly natural thing to do would be to look in the exact opposite direction from where that original mass element was. In other words, extend the blue line until it hits the slab up at the top, and that will define our next mass element. So that will look something like this, and predictably I'm going to label the length of the newly added segment of the blue line as r2. And so we know that we are considering another mass element distance r2 away from the red point, centered over there, but we have to think a little bit about how big to make our new element. So to understand how big it should be, I'm going to add a couple more lines of sight. Rather than going from the center of the mass element to the point of interest, however, I'm going to draw these new lines of sight from each individual corner of our original element. So that's going to look something like this. Our first one will come from the upper left corner, go through the point of interest and end up somewhere over there. Then our second corner is going to do the same thing, but it's going to be inverted, so it ends up sort of above the endpoint of the first line that we drew. Similarly for these other ones, so the top right corner is going to end up at the bottom left, something like that, and the bottom right corner is going to end up at the top left. So we've got the four corners of our mass element defined up there. If I just draw those on, then you can already see that the two mass elements that we have are not exactly the same size. Obviously, I haven't done this perfectly to scale, but it does look like the one at the top there is smaller because the point that we chose, the red point that we chose originally, was closer to the top plate than the bottom plate. Just to label a few more quantities, let's say that the original element has an area on the slab of A1, and our newly created element has an area of A2. So also notice that all of these black lines that I've just added on define two oblique pyramids. And not only that, but those pyramids are mathematically similar to each other, meaning they're basically just different sized versions of each other. If you wanted to prove that, you could use the fact that where the lines meet at our red point in the middle there, you have a bunch of vertically opposite angles. So the upper angles between the edges and faces of those pyramids at the top vertex is the same for both pyramids. Then you can also argue that all the angles at the base of this pyramid, the base of that pyramid up there, are also the same because you have a bunch of Z shapes that you could make using the parallel upper slab and lower slab, and then you would have a bunch of alternate angles, meaning that all the angles of those pyramids are the same and therefore they're mathematically similar. So we should make a note of that. That's going to be a key point in our argument. Let's call this bottom pyramid P1. Let's call the upper pyramid P2. And then we can just write down that P1 is mathematically similar to P2 because of vertically opposite angles and alternate angles. Now, the way similarity works with shapes in 3D or indeed in 2D is that the corresponding areas, the scale factor for the corresponding areas is the square of the length scale factor. And so we've already defined enough quantities on our diagram to write that down mathematically. The area scale factor between these two pyramids is A1 over A2, right? Just the ratio of the areas of the bases. The length scale factor is going to be R1 over R2. That's a characteristic length in each of the pyramids from the center of the base up to the upper vertex. So A1 over A2 would have to be R1 over R2 all squared. If you rearrange that to get the same numbers on the same sides, then you conclude that A1 over R1 squared is equal to A2 over R2 squared. Now, what does this have to do with gravity? Well, each of those mass elements is going to be pulling a test particle and our little red cross there towards itself. You're going to have a contribution of gravitational field G1 pointing towards the mass element at the bottom, and another contribution G2 pointing in the exact opposite direction. Now, if we say that the uniform surface density of each slab is sigma, then we can just come up with expressions for those two gravitational fields. The first contribution, G1, is going to be gravitational constant, big G, times the mass of the element, which is sigma times its area. And of course, gravity is an inverse square law, so we divide by the distance R1 squared. But we've just shown that A1 over R1 squared is the same as A2 over R2 squared. So we could, if we wanted to, rewrite this as G sigma A2 over R2 squared. But this, of course, is exactly what you would get for little g2, the contribution to the gravitational field due to the element up at the top. So when you combine g1 and g2 together, your overall gravitational field is going to be 0 because you have to subtract g1 and g2 because they're in opposite directions, right? So purely because of the fact that gravity happens to be an inverse square law, and because of the fact that we have this purely geometrical fact, right, from the similar pyramids, we can conclude without referring to Gauss's law, which involves the flux of a vector field through a surface, we can conclude quite simply that there's no field between these two plates. I guess the final step in the argument is that we've only considered two arbitrary elements here, but you can imagine sweeping that blue line, what I was calling the line of sight earlier, sweeping that blue line in every possible direction. That's going to define infinitely many pairs of mass elements, but they're always going to pair up, one on the top, one at the bottom. And because we chose our points arbitrarily initially, the contribution to the total gravitational field due to any given pair in any given direction is also 0. So we would be basically doing an integral of just 0 if we were to sum up all of those individual contributions due to the pairs of mass elements. And of course, our red point was also arbitrarily chosen, and so this is valid anywhere between the two infinitely big slabs. As a final thing to consider, what about if you have finite sized slabs instead of infinitely big slabs? Well, in that case, you can't make the same argument about being able to pair up all of the little elements that we made for the infinite slabs, right? If you happen to choose your point of interest, this red cross here, if you happen to choose that being exactly along the sort of axis of symmetry of your system, right in the middle of your two slabs, then you would be able to pair them up. So I'm pretty confident in saying that there should be no gravitational field at the midpoint between your two slabs, even if they're finite. But then if you were to choose a point near the edge, for example, like this, you would have one element up here, and you would be looking to pair that up with another element somewhere over there. But if the bottom slab is finite, then there is no corresponding element there. And so your test particle at the red cross is going to be sort of pulled inwards and upwards towards the upper slab there, which is kind of intuitive. So that's all for now. It's a well-known result, but hopefully this has given you a bit more insight into where it comes from and just a different way of understanding this. So thanks for watching and see you soon.